All right, welcome to This Explainer. Today, we are totally peeling back the onion to discover exactly what Redis is, and more importantly, the brilliant engineering that makes it so incredibly fast. Let's be honest, we all absolutely hate waiting for loading screens or buffering wheels, right? So, if you've ever wondered how some of the most data-intensive applications on the internet just skip those delays and achieve sub-millisecond response times, well, you're absolutely in the right place. So let's dive right into what is honestly a massive counterintuitive mystery. We live in this tech world that is frankly obsessed with multi-core processors. More threads, more concurrency, more speed. Yet how in the world does Redis achieve these blistering speeds? We're talking handling hundreds of thousands of operations per second using primarily just one thread. I know, it seems like it shouldn't make sense, but as we're going to see today, doing less is actually the secret to doing more. Here is our roadmap for today. 1. Meet Redis. 2. The single-threaded secret. 3. Engineered data structures. 4. Memory and network magic. And 5. Scaling without slowing down. Kicking things off with Section 1, Meet Redis, which actually stands for Remote Dictionary Service. Fundamentally, Redis is an open-source, in-memory data structure store used as a database, cache, message broker, and streaming engine. But the absolute most critical word in that whole definition is in-memory. Redis operates entirely in your RAM, completely skipping slow disk access. And by keeping everything in memory, it provides that sweet sub-millisecond latency. This fundamentally blurs the line between a simple cache and a full-blown primary data store. You aren't just caching static rows of data here. You're interacting directly with complex data structures pretty much instantly. Moving right along to Section 2, the single-threaded secret, or doing more by doing less. Let's compare Redis to your traditional multi-threaded databases for a second. Traditionally, databases use a thread-per-connection model, and that means a ton of high-context switching overhead, super expensive thread synchronization locks, and constant cache line invalidation. It's basically a massive traffic jam of threads constantly fighting for resources. Redis, on the other hand, multiplexes I/O on a single thread. It essentially acts like this hyper-efficient traffic cop, rapidly switching its attention between different connections without ever locking up the system. Because it uses a lock-free event loop, you get perfectly deterministic behavior and perfect cache locality. By just completely eliminating the massive overhead of multi-threaded lock contention, Redis's single-lane highway actually moves traffic much, much faster. To put this physically into perspective, the speed difference is just staggering. An L1 cache hit, that takes about 1.2 nanoseconds. Main memory, try 100 nanoseconds. In a multi-threaded system, when different cores modify shared data, they actually force each other to invalidate their CPU caches, a messy process called cache line ping-ponging. This forces the CPU to go fetch data from the much, much slower main memory. But keeping a single thread means perfect L1 CPU cache locality. Redis just keeps its data structures hot right there in that 1.2 nanosecond L1 cache. No synchronization locks, no context switching, just pure, uninterrupted processing speed. Which brings us to Section 3, Engineered Data Structures, the actual building blocks of all this speed. Let's look at something super basic like strings. Redis is written in C, but it actually doesn't use traditional C strings. Why? Well, because to find the length of a traditional C string, the system literally has to traverse the entire string just to find the null terminator. That's an O of N operation that has driven developers crazy for decades. Plus, you can't even safely store binary data in them. Redis solves this with SDS, or Simple Dynamic Strings. SDS pre-stores the length of the string directly in a metadata header. It changes this slow, calculation-heavy operation into instant O of 1 retrieval. It's also completely binary safe. It's a tiny structural tweak, sure, but it saves massive amounts of CPU cycles when you're executing millions of operations a second. And honestly, it doesn't stop at strings. Redis uses these incredibly clever structures under the hood for pretty much everything. You've got ziplists, which store small lists in contiguous memory to completely save on pointer overhead. Then, when lists get a bit bigger, Redis seamlessly switches to quick lists, which are basically hybrid linked lists of ziplists. For sets of integers, it uses int sets, again, continuous memory without the bloat. And for those massive sorted sets, it deploys skip lists. These are probabilistic multi-level lists that allow for lightning-fast O-log-n searches, entirely skipping the heavy, slow rebalancing overhead of a traditional balanced tree. Redis just automatically shifts between these brilliant structures under the hood to perfectly balance memory efficiency and raw processing speed. Okay, Section 4, Memory and Network Magic, specifically jemalloc and pipelining. Think about it. If you're managing millions of tiny data structures, memory fragmentation is going to become a huge bottleneck really fast. So instead of standard memory allocation, Redis uses jemalloc. This is a general-purpose memory allocator specifically tuned to minimize fragmentation and improve performance for workloads with tons of small allocations. It cleanly divides memory into specific size classes, preventing your operating system from wasting fragmented space. For you, this means Redis runs smoothly and predictably without suddenly crashing or hogging all of your server's RAM. Now, what about the network side of things? Every command sent over a network suffers from round-trip time. Send 100 commands one by one, you're waiting for 100 round trips. No thanks. Enter Redis pipelining. Here's how it works. The client starts a pipeline transaction and sends multiple commands sequentially without waiting around. The server then processes them all serially in its event loop, and finally, the client receives all the responses at once in a single batch. By batching commands like this, you completely bypass the massive delays of network latency, vastly increasing your total throughput. Finally, let's hit Section 5, Scaling Without Slowing Down, I/O Threads and Clustering. Now, remember earlier when I said Redis was strictly single-threaded? Well, actually, scratch that. Redis 8 introduces this absolute masterclass in targeted concurrency. It keeps the actual command processing, the core manipulation of your data, strictly single-threaded to keep all those awesome L1 cache benefits we just talked about. But it adds asynchronous multithreading specifically to offload network reads and writes. It also adds targeted SIMD, that's single instruction, multiple data, optimizations for complex calculations, and a new dual stream replication that transfers snapshots and ongoing changes simultaneously. It's applying multithreading only where it helps the absolute most, without ever interrupting the core data engine, and it boosts throughput massively. But what about horizontal scaling, like actually adding more physical machines? I want you to think about this massive number right here, 16,384. This represents the exact amount of hash slots available in a Redis cluster. It's literally the secret sauce to algorithmic sharding. So when you build a Redis cluster, it takes those 16,384 hash slots and distributes them across multiple independent server nodes. Every single key you save gets mathematically mapped to one of these slots. This architecture means you can add or remove physical servers with zero downtime just by reassigning these slots. Each node operates completely independently, isolating any potential hardware failures, meaning a lot fewer 3 a.m. pager alerts for you while allowing you to scale infinitely and maintain that blazing, single-threaded, in-memory speed on every individual node in the cluster. Which brings us to the end of our explainer, and I really want to leave you with this somewhat provocative thought to ponder. In a tech world completely obsessed with more cores, more threads, and complex multithreading, is doing less actually the ultimate secret to doing more? By ruthlessly engineering out synchronization, locks, and overhead, Redis proves that sometimes the fastest way forward is an incredibly focused, single-lane highway. Thank you so much for joining me on this deep dive into the architecture of speed. Keep exploring, and I'll catch you next time.